joining. So this is the last talk for the speaker. So far we were looking at systems and networks. So here's a bit of a twist. So how does one of the most popular applications nowadays, AI and large language models, and how do these systems use these systems, and what are the communication characteristics of it? So it's going to be presented by Dr. Murali Krishna. He's a computer scientist at ALCF. So Murali, please take it. I don't know. You can. Are you on Zoom?
Just share your screen. The rest will be taken care of. Automatically come there. Is there a video that you want to share?
No, please.
You can mute. Yeah.
Thank you. Hello, everyone. I'm Emani from Argonne Leadership Computing Facility. So I'll be talking on some of the more recent work that we have started, kind of understanding large language model training on different AI accelerators. Just started this work few years back, looking at different kind of workloads, and more recently into the LLM space, given a lot of interest and a lot of challenging use cases for that. So here's a high-level snapshot of what kind of work I'm thinking. So we have the experimental facility where the science, actual science runs, and we have the computing facility which houses the supercomputers that we have Aurora deployed, and we also deployed a small-scale AI accelerators, which are like non-traditional or the emerging AI systems, to cater to different kind of applications like simulations or data-driven models. And in our AI testbed, so we currently have these 5 systems. It's an infrastructure for next generation AI machines. The Cerebrus CS2, the Sambanova data scale, the Graph Core system, Habana, and the Grok Rack. So our goal is to understand how these systems perform for a wide variety of tasks, and also help our science teams to port their codes, say if they're running on NVIDIA or Intel GPUs, to these systems to understand, can they do any better? So this kind of a testbed that we have been excessively working on. So a quick high-level summary of how these systems kind of differ. For example, the left-hand figure, so this shows the Sambanova RDU, that's called a reconfigurable data flow unit. So if you see this picture, so that's a single chip which has a bunch of compute and memory units. They're called as PCU and PMU. And you see those blocks here, so that's where the layers of a model, they are kind of mapped onto the chip. And the data flow happens across the PMUs on the chip itself. So it's kind of, you're mapping a data flow onto that particular chip. That's how it kind of minimizes any overheads between the host and the device. And here is a bunch of RDs which are connected to form a data scale node. On the right-hand side, this is a Cerebrus chip that's called a wafer scale engine. It's a pretty massive compute chip that has around 850K plus compute cores. So you see the sheer amount of compute capability that engine has. And this is the picture for the Graph Core IPU. You're looking at the comparison between the CPU, GPU, and IPU. So CPU is mostly for scalar processing. GPU, we have known it's looking for SIMD-based applications. For IP is kind of a more finer level of granularity, with looking at massively parallel MIMD-based architectures. So this kind of gives a high-level snapshot of how these systems differ from the traditional, say, the NVIDIA-based GPU that we are kind of working on mostly these days. So our testbed, we started with the first generation of deployments from all these systems, and we kind of upgraded them to the latest generation of the hardware, along with an increase in the scale. So right now we have 8 nodes of Sambanova RDUs, there are 64 RDUs, and we have 64 Graph Core IPUs, and 2 Cerebrus wafer scale engines, and we have Grok Rack, it's a primary inference-based engine with 72 accelerators. And since we are part of the US Department of Energy and the Leadership Computing Facility, so we have provided access to these systems to a broader community. So anyone who's interested in open science research, they can get access to these systems, try out these machines, and port their applications. And as part of the NSF-based NAIR project, so we also providing resources through NSF. So this is a very high-level kind of architectural and comparison of what the capabilities of these systems have. I'd like to highlight a few of those. So we see those blocks in the red thing. So for example, on the compute units per device, so you see, as I mentioned, Cerebrus has like 850K cores. And again, if you're looking at the memory that's available per node, so the Sambhava SM30 has massive 8 terabytes. So there's a lot of memory availability. And I'm sure there's the different unique characteristics across these platforms. So what this tells us is these systems are totally diverse. They have their so these systems have their own unique strengths and capabilities. They kind of cater to different kind of applications. But again, the main challenge for us is to understand, like, can we do some performance evaluation on these systems to help us, gain more deeper insights out there. So as I mentioned, so we did some studies on diverse set of workloads. And more recently, we also looking at running this LLM-based models, given we are seeing advance in the AI for science use cases, and there's a lot of such applications which are driven by LLM-based models. So we also did some preliminary investigation. Again, this is ongoing work. So the first step we did was traditional deep learning models, and we took core primitive like the GEMS, convolutions, and values, and some standard benchmarks. So this was published in PM-based workshop at SE. I know like one or two systems were again on the first generation system, but again, this was kind of giving more comprehensive comparison of these systems for these particular benchmarks. So we took a similar approach, looking at the large language models. We're kind of looking at different granularity. So first thing is we found what's the core component of this model, which is as a transformer block. So kind of run this, the minimal transformer block as a micro benchmark. Then we took a standard model. In this case, it was GPT-2XL. It's a 1.5 billion parameter model. Again, each of the system can run up to billions of parameters of model, like they're capable of handling much larger models. But to cater to the diverse implementation across the spectrum of the systems that we had, so we chose the GPT-2XL model. And in that, we did some scaling study, figured out what's the impact of sequence length, gradient accumulation steps. And also we ran this science use case, that's GenSLM, which is a foundation model. Kind of ported that onto a couple of these systems and did some performance evaluation. So on the system side, so we used the A100, H100, CS2, SM30, Intel Gaudi 2, the GraphCore 64, Core 64, Grok, and AMD MI250. Try to run like all these examples across all systems, but there's some constraints. So we were able to try to run as many systems as possible. So this is a pretty core transformer block, as you know. So it's has a multi-head self-attention, and it's followed by a feed-forward network with some timing and layer normalization in between. So this is a kind of the core building block for a transformer model. So we just using this particular as a micro benchmark, and we ran this model on the different systems across different precision. So the top graph is showing that the throughput evaluation of this micro benchmark for the forward pass, and we changed the precision FP32, FP16, and FP16. So like some of the key takeaways are kind of high-level arrows there. So we see that for the FP16, we found that the H100 was outperforming the other implementations. And while BF16, we looked at the Sambhava RD was giving a better performance out there. Similar to the lower plots show this kind of a throughput comparison in the backward pass. And again, we found that the Gaudi 2 system was doing pretty good on the backward pass case, and especially with FP32 and BF16. Again, FP16 is kind of predominantly getting better numbers on the NVIDIA H100 system. So as it speaks, so we're kind of looking into more detailed analysis with some profiling, like why are we seeing this difference in numbers across the systems. But again, it's pretty good observation that depending on the system, on the batch size and the precision, so we see this unique capabilities of each system, and I highlighted like 2 examples. So here is the plot here looking at the GPT model performance with OWT dataset. So for this study, we use the same sequence length, but the batch sizes were kind of tuned based on the number of devices that we are running. And again, the software stack is kind of custom built for each system. For example, Cerebrus has their own software stack to run the model, and someone uses Samba Flow. On the A100, we use the Megatron Deep Speed. The Megatron core, which is another main focus area from the NVIDIA library. So this work is still under progress. And even the NVIDIA-based runs are, they need more, the out-of-box runs, and they need like more optimizations. That's currently ongoing work. So here we're seeing the throughput in log scale, scaling across a number of devices. So the yellow bars, we see that the numbers from the 2 CS2 engines. And we see a quick data point. If you kind of look at those performance comparisons, right? So 16 Samano RDUs and 2 CS2s, and again 16 graph core IPUs, so that you get the equivalent performance on 64 A100 GPUs. Again, now say if you're getting the best tuned version on A100 with Megatron core or Megatron LM framework, so we see that this numbers will be much better on the A100 numbers. Some more data points from the scaling behavior. Looking at different systems, the minimum device and the maximum with that we scale. And looking at the scaling efficiency, we found that Gaudi 2 was like doing pretty impressive, getting pretty good scaling efficiency numbers out there. Now, again, as I mentioned, in these implementations, so we took the local batches were kind of tuned. So we kind of observed like what would be the normalized throughput when you are looking at throughputs per unit local batch size. Again, if you see this table, H100 was getting the highest throughput when we're kind of looking at normalizing that with the local batch size. So this table, looking at the impact of sequence length. So looking starting from 1K, and we're trying to increase the sequence length. And across 2 models, 1.5 billion model and 13B model. If you see that one trend, we know that when you increase the sequence length, so obviously it takes a toll on the throughput. Again, it also depends on how many devices that can be used. If you're increasing sequence length, we would definitely need more devices. Now, going to this science use case, the GenSLM. So it's a genome scale language model. So the goal of this application is to understand what are the pandemic causing viruses and how the emerging variants can be determined before, especially with the SARS-CoV-2, kind of identifying what are the mutations, the variants of concern. So the approach here is using the large language models as to learn the evolution. And for this model, so this was pre-trained on pronucleotides, and the model complexity was varying from 25 million to 25 billion parameters. So it's using the GPT NeoX as a core thing, but kind of improved on that. So this model was run on the NVIDIA A100 GPUs, Cerebrus CS2 and Samba SN30. So GenSLM work was awarded the ACM Gordon Wills Special Prize for SARS-CoV research during supercomputing 2022. So this is a quick snapshot of this model, but I won't go into detail. But the table there, if you see, so there's a foundation model and there's also a diffusion model. We're looking at the sequence length, the number of parameters that can be run, and also the data set. The main challenge here from the compute side is scaling these models to handle up to 25 billion parameter models. Especially you see some overheads coming from attention computation along with the communication overheads. We are scaling them across multiple number of devices. So there are a lot more details on the paper, but again, this is a high-level summary for one data point that I would like to focus. So this is for the 13B parametric model, looking at the A100, SM30, and CS2. So we had to run this model on 8 A100s and 8 SM30 RDS, but can run on one CS2. If you see, this is a throughput, tokens per second is improvement. More recently, we also observed like what's the energy efficiency. So if we see this comparison, so at least from the CS2 numbers, so we got it's a 25x improvement on one CS2 versus 8 A100 GPUs. So there's a very big boost in the performance, the throughput numbers, along with significant energy efficient measurement. And again, for this model, the entire CS2 was not being this. We have to be looking 30 to 40%, but it's 40% of the entire wafer that was used for this run. So this kind of shows that for the LLM-based models, there is increasing support for the new AI systems. And again, there are some challenges that I'll show in the next slides. But again, they're kind of showing very promising way of using these systems to run these kind of models. So some of the key observations is, first thing, you're doing this kind of a study, it's extremely hard to get this kind of a fair comparison. So we try to be as close as possible. But again, we believe there are better methodologies that we can use. And for these systems, there's some ongoing support if you're running some open source models and say other architectures. And definitely, if you want to accommodate larger models, so we need optimizations across the stack. So we need some changes like how we implement sparsity from the model side. But again, from the system side, so we know compute was okay, but again, there's significant issue with, say, the memory and the communication. So there's a lot of key focus areas that we need to focus on, trying to understand how we can identify the bottlenecks and kind of figure them out and resolve those bottlenecks. Some of the other issues we looked at were, as I mentioned, each system has their own software stack. So you need to get this model running. But again, getting that to functional state is one. Again, kind of optimizing it is another big challenge. Again, there's a lot of overhead on the compilation times. It might take a while to compile these models. Like it's getting better over time. So we're also kind of looking at focusing on different metrics. Like right now, we just measured the throughput. So, but we want to kind of expand that to include different metrics, like such as performance per watt, which is really important for us. And also looking at some of the other widely used metric, like the model flop utilization, MFU. That kind of tells how well the system is being used. So that would be a better metric. So MFU metric is that's something that we're working on. And to again understand into more details of how these models are being run, so we had to do some profiling studies. So we did some profiling studies with on NVIDIA with Insight systems, and we're also working closely with the vendors to do a similar study across systems. Right now we have for the graph system, we have the Pop Vision tool. We were able to get some profiles. And Sambano as well, so we have the Samba Tune framework. I didn't include those here, but again, we'll be getting more of these profiles to clearly understand where are the overheads being happening, where are the bottlenecks, and how do those vary across different systems, say A100 versus RDU. So that will be more rigorous evaluation. So we are working on that going forward. And other things, as part of the AI test, we're also evaluating the new AI accelerator offerings. And we're kind of most looking at pre-training tasks, but also we want to focus on inference and fine-tuning, which is also gaining importance, especially in the AI for science domain. And we saw a rapid explosion in the open source models like Llama 3, Mistral, and MOE mixture of expert-based models like Mistral. So we are kind of working on this inference and fine-tuning benchmarks across these systems. So there's also a paper we are working on. Hopefully we'll finish that in the next few weeks. So this kind of gives us a more comprehensive view on how these systems stand or when we kind of use the traditional NVIDIA-based GPUs, for example. And for the benchmarks or the phases side, we're looking at training, inference, fine-tuning, and we're kind of getting more science use cases. And the AI testbed, as I mentioned, the resources are open. So if anyone wants to get their hands on the systems, so there's a straightforward way that you can get access to the systems. So this we have this allocation program called as Director's Discretionary Allocation. We call it as DD allocation. It's a pretty short form. It basically asks about what the project is, what's the goal of the project, and what models that are being used, data sets, for example, and any existing implementations. And once you get the allocation, you get access to these systems and also dedicated support from our in-house experts. So you get more hands-on on these systems and help you to port the applications and run them. And also in terms of the outreach and training activities, so we are doing a lot of training and tutorial sessions. So we do it at supercomputing. And again, ASA, we have this training sessions happening. So more recently, we concluded one with Sambanova and Cerebrus. So there is a Graph Core and Grok workshops that are happening in the 1st and 2nd week of June. So they're all virtual workshops. So all the links that you can get it from these portals. Yeah, come up with publications from the AI testbed front. Feel free to reach out if you have any questions. Thank you.
Thanks, Steve. I know that we are standing between you and coffee. It's not a very nice place to be, but we have time for one question if people have any. Coffee's outside. So that's the most important question. Coffee snacks, I mean, IAC keeps you well fed and well watered. So it's outside. Any technical question?
How hard was it to build a coffee? I mean, obviously, like you said, the systems are so diverse.
Yes.
And okay, token count is an interesting metric, but there's a lot behind. And which model of optimization was. So it's very easy also to look at the absolute wrong thing. Because the number, the token number, is assigning a value metric to the hardware, which may or may not be right. So what's the thought on that?
Yeah, as I mentioned, it's extremely challenging to get the right numbers out there. So we're kind of following some, getting that coherent comparison. So kind of fix the model, the parameters, the implementations are the same, and kind of fix the sequence length that we're using. So try to narrow down to get an equivalent implementation across them. But again, there are a few things that we can do. For example, the way the internal optimizations takes place on, say, Cerebrus or Graph Core. So that will be different from what, say, NVIDIA or AMD does. So we are trying to use the respective software stacks to get the best versions on the respective platforms. So whatever numbers that you see, so that should reflect the tuned versions or the tuned implementations for that specific platform. But at least in this, the NVIDIA numbers, so there's still ongoing work on that, but other systems are all optimized implementations. And we're also looking to put all our scripts that we have used, all the data points, GitHub public repo. So that will be useful.
Thank you. So I don't want to hold you from coffee any further. Please feel free to chat with Murali and catch him for coffee if you're available.